Hello, everybody. This is Mr. Fasoni. Today we'll be going through chapter 4.3. Remember that chapter 4 is all about polynomial functions, and chapter 4.3 is specifically about the operation of dividing polynomials. So let's go ahead and get started here. So we've got three goals. Our three goals are to use long division to divide polynomials by other polynomials. That's going to be very similar to long division that you learned in elementary school. Then we're going to use a new type of division called synthetic division to divide polynomials by specific types of polynomials. These types will be binomials in the form of x minus k, or in other words, linear polynomials. And then we're going to use something that comes out of synthetic division called the remainder theorem. All right, so let's get going on this. So concept one, the long division of polynomials. So dividing polynomials is just like long division that we learned in elementary school. It's very similar to it. If we divide one polynomial by another and have a remainder of 0, that means that the divisor divides evenly into the dividend. If there is a remainder, then the divisor does not divide evenly. So for instance, if I've got 15 into 387, I can do long division here. Remember, the outside number is the divisor, and I'll start color coding immediately, actually. The inside number inside this kind of half rectangle is called the dividend. That's the number that's being divided. 15 is the divisor. And if we start dividing out stuff, 15 goes into 38 two times. 2 times 15 is 30. And then we subtract. 38 minus 30 gives me 8. I bring down the 7. And then I just repeat that process again. 15 goes into 87 5 times. 5 times 15 is 75. Subtract, and I get 12 at the end. So my quotient is my answer to my division problem, and anything that's left over at the bottom is my remainder. So this would be saying that I have a remainder of 12. Now I can always continue dividing through and get an exact answer, which we're going to kind of do with polynomial division. It's just that we write our answer a little bit differently. So if I'm thinking about this, I could say that 387 divided by, remember division is just another way of writing a fraction, divided by 15 is going to give me the answer of 25, or a quotient of 25. And I can say it's plus a remainder of 12, which itself, if I want to get an exact answer, is going to have to be, again, divided by 15. So this format, where I've got my dividend divided by my divisor on the left side of the equation, and then my quotient plus a remainder divided by the divisor again on the other side of the equation, this is kind of the format for an exact answer. If I were to continue dividing this last part here, the 12 divided by 15, I could get an exact answer, and I would get a decimal form for this problem. Not all decimals end up being exact. Sometimes you get a repeating decimal. So it's not going to divide into a decimal that terminates, but it will repeat if it does not terminate. All right, so just one thing to note, the degree of the remainder must be less than the degree of the divisor. Just like in normal division, my remainder is always going to be smaller than my divisor. If my remainder is bigger than the divisor, that means I can fit another divisor in there. Just to briefly discuss that, if I were to do this problem, and maybe I didn't know that 5 went into 87, or sorry, 15 went into 87 5 times, maybe I put 4 to start. And I went, okay, well, 4 times 15 is 60. I subtract, and I get 27. As soon as I get to this point, I go, oh, that's not right. I can fit another 15 inside of 27. So I'm going to go back and fix my mistake. I'm going to increase that ones digit by another 1. And now I've got 75. And sure enough, now my remainder is smaller than my divisor. So the same idea holds with the degree. The degree of the remainder must be less than the degree of the divisor. All right. So we've got this notation. We kind of just talked about this with our problem above. We had a dividend of 300, oops, wrong color. A dividend of 387 divided by a divisor, which was 15, and that equaled a quotient, which was 25 plus my remainder, which was 12, over my divisor again, which was 15. Well, the same idea holds here with polynomials, but we just give them placeholder names that look like functions. So I've got a dividend, which is some function f of x, it's a polynomial function. I've got another polynomial called d of x, which is my divisor. My quotient is q of x, and my remainder is r of x. I'm going to be trying to use this color coding as much as I can. All right, so let's set this up. Polynomial long division. We're going to divide 2x to the fourth plus 3x to the third plus 5x minus 1. We're going to divide that by x squared plus 3x plus 2. So how we go about this is we set this up just like normal long division. 2x to the fourth plus 3x to the third. Now there is one thing we have to be aware of. When we set up our polynomials, again, place value is very important. Just like it was when we were adding polynomials, subtracting polynomials, multiplying polynomials, we have to account for the missing values. In this case, I've got a fourth power and a third power, but I don't have a second power. So I'm going to put a placeholder in there for my second power. I'm going to put 0x squared right in there, and then continue with plus 5x and minus 1. That's my dividend. That's the value being divided. My divisor is x squared plus 3x plus 2. And now I'm just going to work through this problem. So as I work through this problem, what I compare, instead of comparing the whole divisor to the dividend, all I'm going to compare is the first value, the highest value. Because remember, we want our polynomials in standard form where the highest degree is first. So x squared is my highest degree on my divisor. I'm going to compare that to the highest degree on the dividend. So I'm looking at x squared and 2x to the fourth. Well, I could very quickly calculate how many times x squared will fit into 2x to the fourth and do some quick division. 2 divided by effectively 1 is going to be a 2. X to the fourth divided by x squared is going to give me x squared. So x squared fits into 2x to the fourth, 2x squared times. Now I'm going to do some multiplication. Just like division, once I have a number up top, or just like regular long division, I should say, with numbers, once I have a value up top, then I'm going to multiply that value by everything in the divisor. So I'm doing 3 multiplications here. Long division can get hairy very quickly, so we have to keep track of what we're doing. So 2x squared times x squared is going to give me 2x to the fourth again. 2x squared times 3x is going to give me 6x to the third. And 2x squared times 2 is going to give me 4x squared. Now we move on to our next step in division, which is just subtracting. I'm going to be subtracting everything that's in orange here by the 3 values that are directly above it, just like we did with long division. But remember, with subtraction, I'm subtracting all 3 of these values, so that subtraction sign on the outside of the parentheses is actually going to flip my signs of all 3 of the terms that are on the inside. So all those positives turn to negatives. And then I'm going to just continue subtracting here. 2x to the fourth minus 2x to the fourth, or I'm sorry, I'm going to turn this into addition. 2x to the fourth plus negative 2x to the fourth is going to equal 0. 3x to the third plus negative 6x to the third is going to equal negative 3x to the third. And 0x squared plus negative 4x squared is going to equal negative 4x squared. Last thing I do for this first cycle through is bring down my next value, plus 5x. At this point, I'm just going to repeat the cycle again. So this time, I'm comparing x squared here on my divisor to negative 3x to the third. And again, I can set that up, or I can do it in my head, whatever works. Negative 3x to the third divided by x squared, well, that's going to give me a negative 3 up top and an x. Because negative 3 divided by 1 is negative 3, and x to the third divided by x squared is x to the first. And now again, I just do that multiplication. This time I'm multiplying negative 3x by all three of these. And I repeat the cycle. Negative 3x times x squared is negative 3x to the third. Negative 3x times positive 3x is negative 9x squared. And negative 3x times positive 2 is negative 6x. Again, I am subtracting that second value. That subtraction sign is going to turn all my negatives on the inside to positives, and then I can turn that into an addition problem. And then I go negative 3x to the third plus 3x squared. These cancel. Negative 4x squared plus 9x squared gives me 5x squared. And 5x plus 6x gives me 11x. Last thing I do is bring down that negative 1. And now I've done that second cycle. So we're going to do this one more time. So now I'm comparing x squared to 5x squared. I'm going to zoom in a little bit. I'm running out of room. Since I'm comparing x squared to 5x squared goes into 5x squared. Again, I can do the division really quickly here. 5x squared divided by x squared. 5 divided by 1 is going to be 5. And x squared divided by x squared is just 1. So all I have up top this time is a positive 5. Again, I'm going to multiply that by x squared plus 3x and plus 2. When I do that, I get 5 times x squared is 5x squared. 5 times 3x is 15x. And 5 times 2 is 10. Again, I'm subtracting. So I'm going to subtract this entire thing. Oops, forgot my sign there. It's plus 10. That negative sign on the outside is going to turn all my positives into negatives. So positive 5x squared becomes negative, plus 15x becomes negative, and plus 10 becomes negative. Let's get rid of the pluses there. Turn this from negative to positive. And again, these cancel. 11x minus 15x is negative 4x, and negative 1 minus 10 is negative 11. This value here at the bottom, its degree is now lower than the divisor. I've got a first degree down here, so I can't divide anymore. I've got a second degree for my divisor. So this last value here at the bottom is my remainder. So if I put this all together, the stuff at the top, that's my quotient. The stuff on the bottom is my remainder. So if I were to write this problem out in the form that we discussed earlier, I could take my dividend, the number that's being divided, 2x to the fourth plus 3x to the third plus 5x minus 1. That's my dividend. I'm going to divide it by my divisor, which is x squared plus 3x plus 2. What I get out of that is I get my quotient, which is 2x squared minus 3x plus 5, plus my remainder. My remainder is negative 4x minus 11, all over my, not all over, just the remainder over my divisor. So again, on the left side is kind of my original problem. my dividend divided by my divisor. The right side of my problem is my quotient in pink plus my remainder in that light blue color over my divisor, which is again in red. And this is how we would write our answers when we do long division. Because we're not dealing with just numbers, we won't end up with a decimal or a repeating value of some sort, a terminating or repeating decimal, I should say. So to get an exact answer, we have to leave it like this. All right, let's move on to synthetic division. So synthetic division is a special situation. When we divide a polynomial by a linear term, a first-degree polynomial, we can use a shorthand version of long division that's called synthetic division. So I'm going to kind of get abstract here for a minute. And we're going to go through this kind of quickly. Oh, doing the wrong colors. I should get my colors correct first. So this is how we're starting off. F of x divided by some divisor, d of x. Remember, f of x is my dividend. I will end up with a quotient, some other polynomial, plus a remainder divided by my dividend again. Okay. So this is how we start. So let's go ahead and replace our divisor, d of x, with an actual form that represents it, in this case of synthetic division. In other words, when I divide my divisor, I'm going to be dividing by x minus k. And the reason for that is that the divisor is a linear. And it's in the form x minus k. So this is what's happening when we're doing synthetic division. We're going to continue along this path in a minute, but let's show how synthetic division works. Synthetic division is this crazy shortcut. So what we're going to do is first I'm going to set up this problem like I would with long division. I've got x, negative x to the third plus 4x squared plus 9. So what I'm going to do is I'm going to set this up just like normal long division really quick, and I'm going to work it through. I'm going to do it very quickly. Expand this. I think I'm going to be taking up too much room. Okay, so I've got my long division set up, and if I want to work through this, I can very quickly. And I'm just going to do the steps without talking through them too much for the sake of time. But if you're confused on anything, you can always pause and compare it to what was done above. So I divided my first time through, I got negative x squared. And then I'm going to go through a second time. X goes into x squared. X times. Now, I made a mistake here. I tried to go quickly. I need to actually keep track of my place values. I've got 0 x's there. So I'm going to go back and fix that really quick. No real harm. It's really a 0x there. Hasn't affected anything. I caught it in time. But now if I multiply through, I get x squared minus 3x. And again, I'm going to subtract. This becomes negative. This becomes positive. And finally, I'm going to bring down the 9. And I'm going to go through one more time with my division. X goes into 3x, well, just plus 3 times. And then when I multiply through, I get 3x minus 9, and I can subtract. And when I subtract, my positive 3 becomes negative, my negative becomes positive, these cancel, and I get 18 at the bottom. So I get my answer very quickly, and that's mainly because I'm relatively fast at this. I've been doing it for a long time, but it's still kind of messy and it still takes some time. But I found my my quotient and my remainder, right? Normal long division, no big deal. Well, we have this nice thing that we can do called synthetic division, which allows us to treat these a little bit differently when I'm dividing by a linear function. So I'm going to set this up again over here on the right. I'm going to keep track of all my stuff again. I have to keep track of that 0x. So I'll set that up. Got my problem set up. So what I'm going to do instead this time, the way synthetic division works, remember, our divisor is in the form x minus k. Well, if it's in the form x minus k, that really means that my k value is equal to 3. It's just going to be the reverse of the sign inside the linear. So I'm going to bring that 3 down and put a little box around it to keep track of it. And then with my divisor, or my dividend, I'm going to bring down all of my coefficients. Negative x to the third becomes negative 1. 4x squared becomes 4. 0x becomes 0. And 9 becomes 9. Now, what I'm going to do is continue bringing things down. Starting with the first value, I'm going to bring this negative 1 straight down. No change to it. Once I've done that, synthetic division becomes a series of multiplying and adding. So negative 1 times positive 3 is negative 3. Then I add 4 plus negative 3 gives me positive 1. I then take the positive 1 times the positive 3 over there for k. Again, I get positive 3. 0 plus 3 is 3. And then finally, 3 times 3 is 9. 9 plus 9 is 18. Now, what does this all mean? Well, if you look at these values here, when I've gone through this little cycle, this last value here on the right, 18, is the same as my remainder. So this far right thing is my remainder. Let me write that a little bit clearer. The far right value is my remainder. If I look at these values, this 3 represents just the number 3. The 1 represents positive 1x, and the negative 1 represents a negative x squared. These coefficients represent the values in my quotient. So this is my quotient, which is the same thing as that. And finally, these values in yellow, I'm going to circle them with orange. This negative 3 here represents the negative 3 that I'm subtracting. The positive 3 here represents the positive 3 I'm subtracting, and the positive 3 I'm adding, and the 9 represents the 9 that I'm adding. So these values here in the middle represent the steps that are going on. And what it results in is a much more compact and quick form of division that can be done only when we divide by a linear. It won't work if I'm dividing by a larger degree polynomial, but it's great when I'm dividing by a linear. Instead of having to multiply multiple times when I'm doing steps across the top up here on the left, I only have to multiply once. And Instead of having to flip a bunch of signs, I don't have to flip any, because when I convert this -3 to a +3, that's the sign flipping being done for us. Switching that negative to a positive before I multiply allows no checking for sign flips or anything like that going forward. So it reduces the amount of steps we have to take. It reduces the amount of errors that we can make by flipping signs, by multiplying through and doing all that stuff. And it streamlines things much quicker. The bigger these division problems get, if I'm dividing, a 5th degree polynomial by a linear, it's going to be a little bit longer, but overall the amount of steps aren't going to increase too much. Whereas with long division on the left, if I had a 5th degree polynomial, I'm going to have more layers down in this part and more opportunities to make a mistake. So synthetic division is much, much quicker. So from that, we get one more concept. We get this concept called the remainder theorem. The remainder theorem says, if a polynomial f of x is divided by x minus k, then the remainder r is equal to the function f of k. So this is where I want to go back to that conceptual stuff that we started. So we know we're dividing by a linear here. Well, logically speaking, if I think about dividing by a linear, if I'm dividing by a 1st degree polynomial, that means my remainder has to be a degree lower than a 1st degree polynomial. If you remember your polynomial types, fourth degree polynomial is a quartic, 3rd degree is a cubic, 2nd degree is a quadratic, 1st degree is a linear, and then below 1st degree we call a constant. And a constant is just another way of saying just a regular number. So any number is a constant, whether it's a whole number like 5 or 10 or whatever, negative number, a fraction, a decimal, an irrational number, any of those can be constants. Well, again, if my divisor is a linear, if I'm dividing by a linear, that means that my remainder is going to have to be a degree lower. It's going to have to be a constant. So what I can do then is I'm going to replace this r of x with just a constant value we're going to call r. So I'll set up this equation again. Oh, and I forgot my plus sign. Okay, so things are changing a little bit. It still has the same structure. So this step, I just said that remainder is constant. All right, so let's do some more work. Let's say I want to get f of x by itself. If I want to get f of x by itself, that means I'm going to have to multiply both sides of my equation by x minus k. So I'm going to go ahead and set that up really quick. Trying to set up my spacing in a way that makes sense. And maybe I'm showing too much here, but I want to make sure that I'm being explicit when I'm writing this out. So this looks like a mess now, but the nice thing is, if I multiply both sides by x minus k, I get some nice cancels. So on this step, I multiply by x minus k. on both sides of the equation. So now I can write this out. Left side of the equation is f of x. My right side of the equation cleans up a little bit now. It's still a little bit complex, but it's looking better. It's x minus k times q of x plus r. So this is just a cleaned up version. Well, next up, cleaning up this little mess here. Next up, what I'm going to do is I'm going to see what happens when I plug in that k value from synthetic division in everywhere that I have an x. So I'm plugging in a k value everywhere that I normally would have an x. So now I've got f of k equals k minus k times q of k plus r. Well, if you think about this very quickly, k minus k for any value subtracted by itself is going to be 0. Or any value minus itself is going to be 0. So if any value minus itself is 0, that means that k minus k is going to have to equal 0. And now I can write out my problem or my equation again. So now I've got f of k equals 0 times q of k plus r. Well, if I've got a 0 there, 0 times q of k, this part right here is also going to equal 0, which means I've got a 0 now here. I have 0 plus r. And f of k still on the left side. And then finally, 0 plus r, of course, that's going to equal 0. Oh, forgot to put my reason for this current step. So the very last step, I get f of k, messing with my colors, f of k equals r. Because 0 plus r equals just r. So what this means then is I can plug that k value, whatever this k value is, when I'm dividing my dividend by a linear, if I plug that k value right into the function, the value I'm going to get out is going to be the exact same thing as the remainder that I would get using synthetic division. So in other words, dividing a polynomial by a linear gives the same result as evaluating the polynomial at k. So this is a lot of abstract work to get this kind of thing, but we want to see it in action and understand where it comes from. So we're going to use synthetic division to find the remainder. There's an extra word in there. When dividing 5x to the third minus x squared plus 13x plus 29 by x plus 4. So this is my dividend. This is my divisor. I want to do synthetic division. I'm going to zoom out for this part. So I'm going to do synthetic division. 5x to the third minus x squared plus 13x plus 29. I set it up like long division just to make sure all my place values are in order. I'm not missing any exponents this time, so I'm good to go. And I'm going to put x plus 4 right there. So remember, x plus 4 is just another way of saying my x minus k value. So that means that if I were to pull the k value out, my k would equal to -4. So k equals -4. I'm going to bring down my coefficients. 5x to the third, -1x squared, 13x, and 29. So I bring those down, and then I set up my synthetic division sequence. Remember, I'm going to be adding values and multiplying values. Bring down the 5 first. 5 times -4 is -20. -20 plus -1 is -21. -21 times -4 gives me positive 84. 84 plus 13 is 97. And then 97 times -4 is going to give me a big number. -388. And then finally, -388 plus 29 is going to give me -359. And as always, you can use a calculator for this stuff. I'm doing it in my head because I don't have my calculator with me. But you can use a calculator for these. I'm not going to force you to do these calculations in your head. So my quotient would be 5x squared minus 21x plus 97, and my remainder would equal -359. Well, the second part of this problem is to show how it relates to evaluating the polynomial. So we're going to evaluate the polynomial. In other words, I'm going to plug this k value right in for my x. So remember, my polynomial is 5x to the third minus x squared plus 13x plus 29. But we're plugging in a -4 for all these values. And this is going to be a little bit messy. Oop. Let's zoom in really quick and let's jam through this. So -4 to the third power is going to be -64. -4 squared is going to be 16, and I'm going to bring and then I'm going to bring down the -4 here. I'm going to bring down the coefficients. I've got a 5 times -64, a negative times the 16, and a plus 13 times -4. Of course, bring down the 29. Now I just do some multiplication. 5 times -64 is going to be -320. Then I've got minus 16. 13 times -4 is going to be -52. And I'm going to add 29. So this now just becomes a series of combining like terms. -320 minus 16 is -336. Then -336 minus 52 is -388 plus 29. Put those together, I get -359. So as you can see, sure enough, when I plug -4 into that function, I got -359, which is the same value as my remainder. So when we do synthetic division with a linear as the divisor, the remainder that I get is going to match the value that I would get out of evaluating the polynomial if I plugged that k value directly into the polynomial. So there's a connection there, and it allows us to not only check our work, but it will also allow us to get some results when we're using something called the factor theorem to try to factor polynomials in the next section. All right, guys, this is it for the 4.3. 4.4 will be coming out soon as well. See you guys later.